Hi, my name is Tracy Sonia Anna Arnold and my metric number is 85946. Material handling systems are very important for industries like agriculture and fisheries to keep operations running smoothly. In Kampong Blawai, Sarawak, fishing is the main source of income, but workers face big challenges. They carry loads up to 40 kg over uneven ground and long distances, which is very tiring, time consuming, and unsafe for them. This project offers a better solution with a new material handling system. It uses modern technology and traditional ideas to make transporting fish and shrimp easier and safer for workers. Fishing is very important to the community. Around 90% of households in Kampung Blawai depend on it for income. Improving the handling system can make their work easier, safer, and more efficient. Using ergonomic design also reduces injuries and helps workers be more productive. The system will be made with strong, corrosion-resistant materials to handle the tough coastal environment. This makes it long-lasting and cost-effective. It also meets food safety standards, so the fish and shrimp stay fresh and clean. In the end, this project is about improving lives, protecting the environment, and supporting the community's economy. In the analysis phase, we assess the current manual handling process for fish and prawns in Kampong Belawai, Sarawak. Workers face challenges like uneven terrain, long distances, and height differences. These problems reduce productivity, increase the need for labor, and create safety and hygiene concerns. Next, we move to strategy development phase. Our goal is to design a semi-automated material handling system to transport marine produce from boats to processing plants. To keep it sustainable and affordable, we chose cost-effective and eco-friendly materials for the design. Finally, in the implementation plan, we propose developing a wagon to carry fish and prawns from jetty to the processing center about 250 meters away. This wagon will integrate semi-automated and ergonomic solutions, making the process smoother, safer, and more efficient. The system will not only improve productivity, but also enhance worker safety and reduce the physical strain involved in transporting marine produce.
A very good day to everyone. My name is Rexirana Robert and my matrix number is 85544. So now let us proceed to the force analysis of wagon. As we can see from this slide, this is the calculation of force applied that we need to move the wagon. Based on the calculation, we need to do three different type of calculation based on three different type of surface, which is sandy surface, concrete surface, and tar surface. As we can see from the left picture, this is the free body diagram of our wagon. The total mass that we have is 540 kilogram, including the load and the frame of the wagon. After doing all the calculation, we can see that the force applied that calculate is 983.8 Newton. After getting the force applied, we can calculate the normal force on point A and point B. Not to forget, we also need to calculate the maximum force applied, which is by using formula coefficient of friction times by normal force at point A. Based on the engineering theory, if the force applied on wagon is lower than the maximum frictional force, it cannot overcome the tendency of the wagon to remain static. So based on this calculation, for sandy surface condition, the wagon is unable to overcome the maximum frictional force, hence it will have trouble to move. So now, let us proceed to the concrete surface calculation. By using the same formula and same step of the calculation, we can calculate the concrete surface by changing the coefficient friction to zero point 0.9. So by looking at this calculation, we can see that the applied force is indeed higher than the maximum frictional force. So, based on this calculation, for concrete surface condition, the wagon is able to overcome the maximum frictional force, hence it will have no trouble to move. Now lastly, for the task surface, same as the previous slide before, we can use the same calculation based on same formula and same step, but only changing the coefficient friction to 0.95. Same as the concrete surface, the applied force on task surface is indeed higher than the maximum frictional force. So based on this calculation, for task surface condition, the wagon is also able to overcome the maximum frictional force, hence it will have no trouble to move.
Hello, my name is Edison Dingemang. My matrix number is 83044. So let's see the calculation for the drag force. We know from the project description that the distance from jetty area to processing area is 250 meters. The minimum time travel, assumingly, is 6 minutes or 360 seconds, whereas the maximum time to travel is 720 seconds. Now we can calculate the minimum and maximum velocity of our wagon, which is 0.69 meter per second and 0.35 meter per second respectively. And we can look for the corresponding drag coefficient of our wagon from the dimension of the frontal area, which is 2.1. And can calculate the minimum and maximum drag force using the formula Fd equal to 1 over 2 rho v square cd a. And the minimum drag force is 0.048 Newton, whereas the maximum drag force is 0.186 Newton. Since we are going to install an electric motor for our wagon, we need to calculate the power requirement. Using the formula P equal to Fv, or power equal to force times velocity, the minimum power required to be delivered by the motor is 0.0168 watt, whereas the maximum power is 0.128 watt. Now let's look at the stress analysis. The FBD is the FBD for the base plate for the wagon's bucket. So the load of the Sasaujo, which is 400 kilogram, to find for the weight, just multiply it with gravity acceleration. So the value is 3,924 Newton. And the load is in a distributed form. So the value is 2,207.25 Newton after multiplying the weight with the length of the base plate. So to look for the concentrated load, just multiply it back with the distance of the base plate. So the force is 1,242.68 Newton. Using equations of equilibrium, we can look for the responding force at A and B, which is 621.34 Newton. And now calculating for stress, we just divide the force with the area, and it is 2.21 kilopascal. Since the bucket is decided to be made of aluminium, 2014 T6, the yield strength is 414 MPa. And the groups decided for the safety factor of the wagon is to be 2. So we divided the yield strength with the safety factor, and we get 207 megapascal for the working stress. And since the stress is less than the working stress, the design is safe to be used.
Hello, I am Rodisa Mana Francis, and my metric number is 85560. The trace diagram and the component analysis focuses on identifying and analyzing the components of the material handling system and their interaction with the external environment. The system components consist of the wheel, wagon bed, handle, motor, and frame, which form the essential parts of the material handling design. Each of these components plays a critical role in ensuring the system functionality. For example, the wheel is essential for mobility, the wagon bed supports the load, the handle provides control, the motor offers power for automation, and the frame provides structural stability. These components work together to achieve the overall goal of efficiently transporting loads. The external element or environmental problems that affect the system performance are represented by the supersystem components, which include moisture, sand, roads, and rain. For example, moisture and rain can cause corrosion or reduce the durability of components, while sand and uneven roads can increase resistance and impact mobility. The interaction between the system and the supersystem components highlight the need for a robust and adaptable design. Finally, the product represented as the load is the ultimate outcome that the system aims to transport effectively. The diagram emphasizes the need to align the system components with the external factors to ensure safe, efficient, and durable load handling under varying environmental conditions. This analysis provides the groundwork for creatively enhancing the material handling system by choosing suitable materials, optimizing component design, and addressing outside obstacles. This diagram illustrates the functional relationship and potential weakness within a wagon system, highlighting both useful and harmful interaction. The system consists of key components such as the motor, wheel, frame, handle, wagon bed, and load. The motor rotates the wheel, enabling movement, while the frame holds the wheel, wagon bed, and handle. The load is supported by the frame. External factors like road, sand, moisture, and rain impact the system efficiency. The road facilitates movement, while sand weakens the wheel. Moisture and rain introduce corrosion risks, affecting the wagon bed, frame, and load. Excessive moisture weakens the motor, while rain contaminates the load. The diagram differentiates between normal useful functions, excessive useful functions, and harmful effects using different line style and error indicators, providing a clear visual representation of the system limitations. Next, the diagram presents a structural breakdown of why the wagon's load capacity cannot be sustained. The root causes are divided into 4 key issues, which are the frame breakdown, wheel failure, wagon bed instability, and motor inefficiency. Frame breakdown occur due to weak structural integrity or excessive vibration, which may stem from an insecure frame that does not conform to other components. Wheel failure is attributed to an insufficient number of wheels to support the load and the penetration of small particles into wheel bearings, impairing performance. The wagon bed is unable to sustain the load due to a lack of structure, sturdiness, and excess water accumulation with the produce. Lastly, motor inefficiency arises from a high motor to wheel gear ratio, preventing the wagon from effectively carrying the load. The analysis provides in-depth understanding of the limitation of affecting the system performance and durability. The House of Quality HOQ diagram is a systematic tool used to translate customer requirements into technical features for a product or system. In this particular HOQ diagram, the focus is on designing an efficient material handling system that aligns with the needs and expectations of customers while addressing technical constraints. The customer requirement, Room 1, which includes factors such as eco-friendliness, life cycle, cost efficiency, and resistance to corrosion, form the foundation of the HOQ. These requirements were prioritized based on customer input, with the highest priority given to the product's dimension, followed by cost efficiency, weight, and robustness. These priorities guide the development process to ensure the design meets the most critical customer expectations. The technical requirements Room 2 provides a set of measurable attributes, including the product's dimension, weight, life cycle, cost efficiency, eco-friendliness, and resistance to corrosion. These features are directly linked to customer requirements and serve as a foundation for the design process. Each technical requirement was developed to ensure the system performs optimally under varying conditions. The correlation metric Room 3 identifies the relationship between technical requirements. Positive correlation are marked as positive or double positive, while negative correlations are marked as double negative. For example, the relationship between dimension and weight is highly positive, which are the double positive, indicating that optimizing dimensions can enhance weight management. Meanwhile, the relationship between robustness and weight is neutral, negative, suggesting that improving one might negatively impact the other. These correlations help designers understand how changes in one technical requirement affect others. In Room 4, the relation metric connects customer and technical requirements. Each technical requirement is evaluated against a customer needs to determine its contribution to fulfilling them. For example, dimension and cost efficiency are strongly linked to customer satisfaction due to their high impact and overall functionality and affordability. This ensures that technical efforts are aligned with customer priorities. The importance rating, Room 5, quantifies the relative importance of technical requirements. Based on the metric, dimension has the highest importance rating of 171, followed by cost efficiency at 144, weight at 138, and robustness at 93. These ratings prioritize areas of focus for the design and development process, ensuring resources are allocated efficiently. The customer assessment of competing products, Room 6, evaluates the system performance against competitor offering. This analysis involves customer feedback on competitive products, ranking them based on features such as life cycle, cost efficiency, and eco-friendliness. Additionally, it identifies any unaddressed technical requirements that the new design can meet, ensuring it outperforms competitors in critical areas. In summary, the HOQ diagram provides a detailed framework for designing a material handling system that balances customer satisfaction and technical performance. By aligning customer requirements with measurable technical attributes, identifying correlation, and assessing competitive products, the HOQ ensures a systematic and customer-focused approach to product development. The prioritization of features such as dimension, cost efficiency, and weight ensures the final design is robust, cost-effective, and adaptable to various environmental challenges.
After reviewing all 5 designs, we have chosen Concept Design 1 because it offers the best combination of simplicity, reliability, and practicality. The straightforward design means it's easy to manufacture and has fewer parts that can fail, making it reliable for daily use. It's also low maintenance, with quick, simple repairs that don't require special tools. The design is stable, even when carrying heavy loads, which is great for uneven terrain. Plus, its lightweight structure makes it easy to handle, even in tight spaces, ensuring it's usable in different environments. While the open structure does expose the load to weather, this can be managed with covering or containers. Overall, Concept Design 1 stands out for its ease of use, stability, and reliability, making it the best choice of our needs.
The PU metric presented is a decision-making tool used to evaluate and compare multiple design concepts based on various weighted criteria. Each criterion is assigned a weightage according to its importance, with higher value indicating greater significance in the decision-making process. The criteria include durability, 3, mobility, 5, ease of loading and unloading, 4, storage capacity, 5, weight capacity, 3, food safety, 5, affordability, 4, and lightweight design, 3. Each design concept is rated relative to a baseline using values of 1, better, 0, same, or -1, worse for each criterion. The total score for each design concept is calculated by multiplying the weightage of each criterion by its respective rating and summing up the values. Based on this calculation, Design Concept 1 achieved the highest score of 25, making it the most favorable option. Design Concept 3 and 5 both score 3, indicating moderate viability but requiring some improvements. Design Concept 2 scores -3, showing a weaker performance, while Design Concept 4 scores -11, making it the least favorable option due to significant drawbacks in multiple criteria. From the analysis, Design Concept 1 is the best choice as it outperforms other alternatives in most criteria, making it the most optimal selection for further development. Although Design Concept 3 and 5 perform reasonably well, they may require certain refinements. Meanwhile, Concept 2 and 4 are not recommended as they have negative performance scores indicating they do not meet the desired requirements effectively.
So as an overview, the final design is a motor-assisted wagon that operates similarly to a wheelbarrow, whereby it is designed to be pushed from the back by an operator. So to enhance its usability and efficiency, the wagon is equipped with a motor powered by a 105 or a 103 Ah battery, which significantly reduces the physical effort required to push the load. So the material used for the bucket is aluminum alloy, which is coated with Teflon or PTFE, which prevents water and other liquids containing hydroxyl and oxygen from being absorbed, allowing the bucket to be rated food safe. The frame of the wagon is made from mild steel, ensuring the durability and strength required to handle the loads of up to 500 kilograms, while maintaining structural stability. Loading and unloading operations are streamlined with a front loading and tilting mechanism where upon the destination, the wagon employs a forward tilting mechanism hinge at the front, allowing the bucket to be tilted smoothly. This mechanism enables fast and safe unloading of the produce without causing damage and spillage, so it ensures the sea produce remains intact. It also minimizes physical strain on the operator, making the unloading process both ergonomic and efficient. So here you can see where the motor and the battery is placed. The battery is placed just below the handlebars to act as a counterweight, and the motor is placed next to the front wheels to move the front wheel. The wagon's mobility system includes a handle fixed to its frame and a swiveling caster mechanism, which allows for easy maneuverability, especially in tight corners. The motor is attached to the front wheels, which assists in moving the wagon effortlessly, even under full load, which ensures smooth operation across the operated terrain, which includes sandy, concrete, and asphalt terrain. The storage capacity of the bucket is designed to hold up to 500 kilograms or a volume of 180 liters, which exceeds the 141 liters required to carry the 400 kilograms of shrimp. This ensures the wagon can handle its intended load efficiently without compromising on performance. So in terms of ergonomics, the handle is modeled after a wheelbarrow, and so this design is not only ensures efficiency in operation but also minimizes muscular strain for the operator, which allows extended usage without discomfort. The wagon's combination of ergonomic designs, motor assistance, and ample storage capacity ensures that it meets both functional and user-friendly requirements. So here is a detailed illustration of the final design with units of measurements in millimeter. So among the advantages of this design is that it is motor assisted. System reduces the physical strain of the operator, making it ideal for long distance transportation. The use of Teflon coated aluminum alloy ensures the corrosion resistance and hygiene, extending the wagon's lifespan. And swiveling caster mechanism enhances maneuverability, making it easier to navigate tight spaces, while the large storage capacity of the bucket efficiently accommodates the required load of 400 kilograms. The ergonomic handle design ensures the operator comfort even during prolonged uses. So overall, the final design is an effective solution that combines functionality, durability, and user convenience.
This semi-automated material handling system is a breakthrough for Kampong Belawai's fishing community. It addresses challenges like uneven terrain and heavy labor while ensuring safe, efficient transport of marine produce. The system is ergonomic, reduces strain on workers and uses corrosion-resistant, eco-friendly materials making it durable for coastal conditions. This innovation improves fishermen's livelihoods, boosts productivity and supports sustainable growth in the community.
So that is all from our group. Thank you for your attention.